But this year, assuming that I don't know why I suddenly had this
nearly irresistible.
You're live.
Hey everybody, it's 7:15 on the second Friday of the month, and that means it's time for the Madison Astronomical Society to meet here at UW Space Place. It's great to see everyone who braved the weather tonight. Some people are staying home because there's been a lot of weather going on, and we hope everybody's safe. Just going to run before we get to our guest presentation tonight. I'm going to run through some announcements here. First of all, I see Rick Wayne here. I would like to thank him. I'd like to thank him for volunteering to serve as the chairperson of our ad hoc public outreach committee. And the public outreach committee, occasionally we get libraries and schools and organizations throughout the area check out our website and say, hey, it would be really great to have some stargazing at our venue sometime, or at our school, or at our library. So they send that an email to our website, and then we wind up getting some organization with the help of Rick Wayne to kind of.
There are two phrases that have never been said together. Some organization and Rick Wayne.
But anyways, that's where you're at now. So thank you very much. And occasionally, from time to time, we do have some of these opportunities that comes up. We have some people who participate in our ad hoc public outreach group. That if an opportunity comes up, the people that are a member of that group might will get an email saying, hey, are you interested in doing this? Or if it's something where we want to try to get even more volunteers, we'll just announce them the normal way we do announcements, and Rick will be our contact person. So thank you very much, Rick, for your help and all the past contributions with this ad hoc outreach committee has been working really great, and Dan's also helped organize that. But yeah, we're kind of passing the torch to Rick a little bit. So thanks again. So it's segueing right into some future club events. We're on Saturday the 26th. We are going to have our monthly star party at Yana Research Station. So on July 26th, there will be a weather call at about 4 p.m. And if the weather is good, hopefully a bunch of us will show up at Yana Research Station. If you have any questions about the monthly star parties, send me an email at dyermore@charter.net. On Friday, August 8th, we're going to have our next monthly meeting right here at 7 o'clock at Space Place. And UW-Madison Assistant Professor of Astronomy, Kate Greyer, will give a special presentation titled The Monsters of the Universe, Supermassive Black Holes and Quasars. John, do you want to say a little something?
No, I don't have much more than that.
All right. So, yeah, those massive black holes and quasars have been in the news from time to time lately, and it should be a really exciting and interesting presentation. Now, keeping in line with what I was just saying about public outreach, on Saturday, August 16th at 8 p.m., we are going to have a public outreach star party at Donald Park, and that's nearby Mount Horeb and closer to Mount Vernon here in Dane County, where it's kind of a fun event where we try to pick a Saturday closest to the peak of the Perseids meteor shower, and we set up some telescopes there, and a lot of locals from the area show up and hang out with us. So it's a lot of fun. So contact, if you're interested in participating with that, contact Rick Wayne. And his contact information is in the monthly announcements. So right after that, on Tuesday, August 19th, there's going to be another public outreach star party at Cole Park nearby Lake Mills, and that's on Tuesday, August 19th at 8:15 p.m. And I guess there might be a public presentation that starts at 8:15, and stargazing will start at up at 8:45. Rick, did you want to say anything more about that? Or?
If anybody has ideas for a public presentation, lay them on me.
All right, we're looking for ideas for a public presentation, so.
Or volunteers, even better.
Very good. And then save the date for now. It's kind of off into the future a little bit, but on Friday, October 3rd at 7 p.m., we're going to have Moon Over Monona Terrace. And this is like one of the biggest public star parties in the country. So on the roof of the Monona Terrace Convention Center. It's fun every year. So save that date on your calendar, Friday, October 3rd. All right, I guess you had an announcement you wanted to make?
Many of you remember Tom Furch.
Oh, no.
No.
Oh, okay.
Many of you know Tom Furch, okay. Still know Tom Furch is around and kicking. But he's going to be selling his house, and he asked me to make an announcement that anybody who wants to buy a house complete with an observatory. He lives in Verona, and the details are still being worked out. But if you're interested in that, you can contact me. Just send me an email through the club website, and I'll get the email. I can give you more information. So.
I see some puppy dog eyes back there. Somebody's putting on the most.
It's worth noting that not only does the house have its own observatory, but due to some possible act of corruption, because he was the mayor, all of the streetlights, I believe, on a street were moved to the other side of the street.
That is correct. I
I
forgot.
can do that to my neighbor's floodlight, like.
Yeah. All you have to do is run from Aaron Woods. And there you go. All right. Oh, yes, sir.
Yeah, I just wanted to ask, does anybody know Brendan Flores? He's a prospective new member of the club, and I've been trying to get a hold of him.
Oh, Brandon,
Brandon,
yes.
if you could have him get a hold of me, please, I appreciate
Sure.
it. I don't have, do you have his email address?
Yeah, I think so. I
Well, if you-
text him for sure.
Okay, if I can get his email address, that's all I need.
Okay,
Thanks.
cool.
All right, very good. Does anybody else have any announcements that they'd like to make, or some recent observing experiences or news that they would like to share? Anyone? Is there anybody here who has never visited us at Madison Astronomical Society before that would like to introduce themselves?
I haven't
Oh,
been before.
all right. I'll be right here. I'm speaking through the mic because we are webcasting, and they can hear what you're saying.
Oh, okay.
What's your name?
My name's John Frandy, and my friends Craig and Norm brought me along because they've been talking about this club for a long time.
Oh, John, that was?
John.
It's great to meet you, John. Where do you live in the area?
I live in Lake Mills,
Lake Mills.
same as these strangers over here.
All right, so yeah, you might want to join us, if you jot down the date for that.
Corth Park. Yeah.
Corth Park, yeah, event. That'll be really neat.
Yeah, absolutely.
Yeah, one of the advantages of associating with the club with Madison Astronomical Society, and this is a word from our sponsor, that if you're interested in dipping your toe into this amazing hobby and you're not sure where to begin, well, hang out with us and you'll find out where to begin and how not to spend too much money and buy equipment that we refer to as hobby killer
We
equipment.
give lessons in how not to spend too much money.
Well, it doesn't work out.
I've got good lessons.
Get lessons in how to spend the money, too.
Now, those who do, those who cannot do, teach. You see, I spent too much money too, so therefore I teach. Yeah, and especially members of the club, we have access to our dark sky observing site in northern Greene County, about 30 or so minutes drive from where we're at here. And if we have a star party and you're there and you get to see all these people that are using all different kinds of equipment and things, and you can kind of see how things work. So it's a great club to belong to. All right, I guess announcements went kind of quickly. You've got about 5 minutes to kill a little bit. And I've run out of stuff.
We can go to the presentation.
I think we can start a little early.
Yeah, we can start a little early.
It's not in the bylaws.
Yeah. Oh, we can have a last minute ad hoc bylaws amendment to start the presentation 5 minutes early. John, would you like to come up and introduce tonight's guest speaker?
So before I introduce, I'll chew up a little bit of that 5 minutes by going back to Tom Furch. Tom is a former president of the society, and Tom's observatory in his backyard has an MAS dome on it. When the Art Coster Observatory got a new dome in the 90s, Doc Greiner bought a pro dome to put on that building. The old dome, made out of tin and a lot of duct tape and twine, was going to be discarded, and Tom had it transported to his house, completely refurbished it, and that is the dome that's on his building, an MAS dome on your own observatory in Verona. Ron, just buy a second house. By way of introducing tonight's speaker, some of you know that I love to go outside the astronomy department to find speakers who are doing things that are of interest to those interested in astronomy like us. And so this is about a year ago. I must have been doing a search on the UW-Madison site, and I must have been searching for the term exoplanet, probably searching for a lot of different terms. And Hannah's webpage at Oceanic and Atmospheric Sciences popped up. And so I went to her biography. Most faculty members have a little biographical sketch. And I read it. And Hannah's biographical sketch, it was about a paragraph long, but in the middle of the paragraph, Hannah says, "My first love is astronomy." And I said, "What?" So I immediately sent an email to her and said, "I don't care what you talk about. I'm sure you've got great talks, but we need to get you to our meeting." That was a year ago. It took a year because I scheduled pretty far ahead. And here we are tonight. I've had this one circled on my calendar. My first love is astronomy. It just kills me. She's going to talk a little bit about that in her talk tonight. But I want you all to join me in giving a warm welcome to Hannah Zanowski. Thank you. Oh, and while Hannah's getting her mic turned on, I'm going to ask that if you have questions, try to hold your question until the end. But if you do have a question and you want to ask during the meeting, wait for us to get to you, and I'll have the microphone, so wait for us to get to you. Thank you. Hannah.
Okay, well, this is very on, so, oh my goodness. All right, I imagine you can hear me quite well. All right, so I like to flail a lot when I talk, so if I hit the microphone, well, you'll just deal with it. And I'm getting a little crispy here already. My goodness. I'm an assistant professor in the Atmospheric and Oceanic Sciences department at UW-Madison, and I have kind of been there since 2021. And so today I'm going to talk to you about the ocean's role in Earth and exoplanet climates. And really what I'm going to do here is give you a crash course in Earth oceanography, because any opportunity I get to spread the gospel of the ocean, I absolutely will take it. Okay? But we're going to use that sort of knowledge to then kind of think about how we might apply this in a completely different context of exoplanets toward the end of this talk. All right? But to start though, I am actually going to introduce myself and my research group. there. You know, you cannot observationally constrain that. You cannot direct image an ocean on any exoplanets, but we also have quite a few oceans in our solar system outside of Earth as well, most likely. So why stop at one ocean? Study them all, right? That's kind of what I like to think about. So I've started to kind of branch out off of planet Earth more recently. As a professor, I do a lot of other things besides research, and I actually like to bring that up because there are things that I really enjoy about my job as well. I really love teaching and mentoring, and I do quite a bit of that. So the major classes I teach are a grad level class on research computing and atmospheric and oceanic sciences. So I teach people Python for Earth science data analysis, basically how do you basically learn the tools that we need to do our jobs on a daily basis, right? So all sorts of really fun things that we do within that. It's a very hands-on class. This is my fifth year teaching, I don't remember anymore. I teach a 400 level advanced undergrad oceanography class. That's the fundamentals of physical oceanography. So this is where we really dive into the Navier-Stokes equations. We think about, yeah, oh yeah, we get real in Earth science. Where we really kind of think about how the physics of how the ocean works from that sort of mathematical context and build that up for them. I teach a 100 level, very introductory oceanography class for non-majors. This is like your big, you know, multi-100 person class where you're just telling them the ocean is cool, you should think about the ocean, you should care about it, it's not just water, it really matters for your life every day, kind of course. And then recently I've also started teaching a 1-credit seminar on scientific communications in the atmospheric and oceanic sciences, which is literally about teaching people how to write science. So how do you do scientific writing? That's not something we necessarily come into graduate school with that skill set. So kind of help them think about how you would write your first journal article or how you actually communicate your science to scientific audiences. It's a little bit less about public outreach and that sort of public-facing piece of communication. I'm also involved in the Wisconsin Center for Origins Research, which is kind of this new center that we've kind of developed on campus in the last couple of years. It became official last fall. So this is all about thinking about the origins of life on planet Earth and in the universe. And the Atmospheric and Oceanic Science Department is one of the founding departments for it, and I am our liaison for that. I am our member representative, and I've been kind of instrumental in helping getting this program off the ground and making sure that AOS in particular has a voice in thinking about origins research. Because it doesn't actually as much as you think it should, as it would, right? And then the last piece here is I run a research experience for undergraduates program. It's called STORM. It's Student Training in Oceanography, Remote Sensing, and Meteorology. This is where we bring undergraduate researchers from across the country to our department to get research experience throughout the summer. So just like the astronomy department has an REU that you maybe are more familiar with, since you mostly get astronomy professors talking about this, I started an REU within my department in the first year that I came there. And it's the first REU in my department's 75-year history. It has run for 2 years now, and then we'll be running the third one this coming summer. So, love to think about undergraduate education, really think a lot about all of these pieces together. So I've got my hands in a lot of different pots at this point in time, and there's always more to do, and so I have to learn how to sometimes dial that back. All right, so my academic path, so I grew up in Arizona, and I went to the University of Arizona for undergrad. I got my BS in physics and mathematics there. I actually started out as an astronomy major. We'll come back to that in a second. I got my PhD from Princeton in 2016 in atmospheric and oceanic sciences. So at U of A is where I stumbled across oceanography later in my undergrad and realized that I really, really liked it. And so I thought it was fascinating. I did a postdoc at the University of Washington, second postdoc at the University of Colorado Boulder, until finally landing here as an assistant professor at the University of Wisconsin, Madison. So it's been quite the academic journey, a number of different states that I've lived in to kind of get to this point. Right? So when I went to the University of Arizona, I went there because I wanted to do astrophysics. So my first love really is astronomy. And one thing I really wanted to have today that I don't have is there's this very specific picture I wanted to bring, but I think it's in a family photo album somewhere back in Arizona. It's a picture of me and my dad sitting outside with our janky telescope, you know, back outside by the mountains in Flagstaff, waiting for night to fall to watch the Perseid meteor shower. And so when I was young, especially even as a teenager, we would go out every August together to watch the sky. And we'd just sit out there, watch the meteor shower, talk about everything you could possibly think about, right? When you sit out under the stars like that, that's what gets you talking for real, right? You're really thinking about the deep things. It's a really, really wonderful way in which my dad and I have always sort of connected. And I've really wanted to do astronomy since I was a child, right? So that didn't quite work out for me as an undergrad, partly because I got mono, hilariously enough, my freshman year, and that put me, was going to put me behind in my astronomy major. And so what I ended up doing was, I was like, I'm too straight-laced to handle finishing undergrad in more than 4 years, because I was that type of person. What I decided to do was do physics and math instead, and then potentially come back to astronomy later. So, like I said, my career plans to follow my academic path. I was like, well, I'm going to do astrophysics, and then, well, here I am. I'm an assistant professor and mostly a polar oceanographer, right? So, you know, it's been a very windy road. There was a lot of self-doubt in that process. There still is. That's just part of being who I am, part of being a professor, part of questioning, you know, and pushing the boundaries of knowledge, right? So it's been a journey, and I think it will continue to be like this. And yes, I drew this myself. Thank you. You can, you know, if you would like to buy that art, I can, you know, I can sell it to you. But it's been a wild ride. But I've kind of ended up, in some ways, in this really, really interesting way, coming back now a bit to astronomy with this exoplanet bent that I'm doing. Like I said, I'm still an oceanographer. That's my training, but you know, here I am, right? So. My research background, definitely not exoplanets. I did all oceanography, right? So this started in graduate school. I started thinking about changes in the Antarctic sea ice and their connection to the very deep parts of the ocean. As part of that, I actually got to go on a research cruise to Antarctica. So I spent 2 months at sea, collecting measurements, learning about the ocean, and seeing what it's like to live in the very bottom of the world for a period of time. It was a really, really neat experience. I have studied ocean variability in the West Antarctic. I have thought about El Nino-driven velocity changes in the Pacific Ocean with observations, monsoon-driven changes in the Indian Ocean, and then all the way up to Arctic, thinking about Arctic oceanography, Arctic climate change, then some paleoceanography, so thinking about sort of more recent paleoclimate, thinking about like the last glacial maximum to present day, which is about 21,000 years ago to the present, right? So the evolution of the ocean from that time period when we had, you know, ice sheets covering most of the northern hemisphere, right, all the way down to close to here, but not quite here, right? So that's what the driftless, that's why the driftless exists, right? Because it didn't get covered in ice sheets. But that's also why it's flat here. It's very flat. And when you grow up west of the Rockies, you're kind of a jerk about that, as I've learned, right? So I have studied a lot about the ocean in these different contexts, both from an observational perspective as well as, you know, a climate modeling perspective. Oops, and I have a slide in here that's not supposed to be here, but that's fine. This one is. So when you go to Antarctica, caution, it makes you totally insufferable about having gone to Antarctica. So there's a picture of Emperor penguins that I took myself. It's been 10 years since I've been there, and I swear I will spend the rest of my life trying to get back to that place. It is a uniquely amazing and beautiful and sort of pristine world. And it really feels like you're on a different planet, like absolutely remarkable. Not do it necessarily as a tourist, because I don't love that piece of it from an environmental perspective. But, you know, to each their own, right? So I'm going to skip this, because this was accidentally in here. And so I have some questions for you, because I like audience participation, right? So one thing I want to ask you is, how old is the ocean? So if you read my abstract, and this is not a test, it's okay if you didn't read it. Does anybody actually know how old Earth's ocean is?
3 billion.
I go more north of 4 billion.
Yeah, so it's north of 4 billion. That's actually true. Yep, so it's about 4.4 billion years old, right? So good guesses up in here. So I did say billions earlier. And so if you know its age, and now that you do, are you surprised by that number? Is that something that's shocking to you, or you're like, no? No? Yeah? Okay. See some, maybe not. Had no idea, no context, not sure.
Wasn't there a lot of smacking still
There
going
was
on?
a lot, right? So it may have like evaporated for some time and then come back. And like the Hadean Eon, which is, you know, the 4.6 to about 4 billion years ago, is very, we really don't know a lot about that time period other than like Earth formed, the moon was like, yeah, let's go crazy, we'll do our moon forming impact or Thea or whatever it was, right? And then maybe the late heavy bombardment, maybe not, pick your camp. And then, there were probably oceans though. And so like the more modern research has suggested that oceans have been around for about 4.4 billion years, right? So basically the age of our planet. That's incredible to me. That always blows my mind when I really start to think about that. Like sometimes I go outside and I stare at the moon and I just sit there and think that the moon has been able to just see this incredible amount of change that has happened on our planet for all of those billions of years. Like, I wish I could just, talk to it about what it's seen, Tell me your story, just kind of sitting out there. It's this constant thing. I love that about it, right? It's like this mind-boggling aspect about it. And then the last thing is, what is something else you know about the ocean? Anything. This could be anything that you know about the ocean.
It's wet.
There's salt, yes. It's wet, right? Okay. Yep.
Remarkably, the salt composition of seawater is the same as the salt composition of blood, roughly, human blood.
I don't know that I actually knew that. Damn, I guess that's it. All right, yes, I learned
I learned
something
that in
new
grade
today.
school. It was other way around. It's like, what can you tell me about blood? Well, it's like
Right, you're like,
seawater.
tell this. Like, I got this. But yeah, those are all good things, and those are all things that are important about the ocean. So thank you for throwing some things out there, right? It's always interesting to see what people focus on. But the salt is a good one, right? So, like I said, the ocean formed 4.4 billion years ago. And this is my really, really, really rough idea or rough timeline of Earth's history. So we're missing basically all of these events, a lot of major events in here. This is not meant to be like a comprehensive, explanation of everything that's happened on our planet, right? So we've got this Hadean Eon, which is about 4.6 to 4 billion years ago, that goes from the beginning of basically Earth's formation, right? We've got the formation of the ocean, maybe the first plate tectonics pretty early on, at least the first potential land masses and continents, possibly in the Hadean. There may have been periods of atmospheric haze as well. So basically just sort of particulates in the atmosphere that might block some of the incoming solar radiation. The Archean then is about 4 to 2.5 billion years ago. I'm getting more interested in thinking about the ocean during this time period, so when things have calmed down a little bit more to keep a stable ocean. And again, we haven't managed to get rid of it in this 4.5 billion years, right? Pretty cool, right? Maybe some snowballs, so some total Earth glaciations within that time period, especially entering into the Proterozoic, which is about 2.5 to about 540 million years ago. Big thing here is the development of oxygenic photosynthesis, right? So the great oxygenation event when Earth first formed, our atmosphere had no oxygen in it, right? So it was mostly carbon dioxide and nitrogen and potentially methane and some other greenhouse gases, right? So that helped to keep it warm, helped it to keep the ocean from completely freezing, or even that's what's invoked because the sun was a lot fainter in the past, right? Maybe the first supercontinent in the Proterozoic, maybe in the past. There's a lot, it's really hard to get geological records from this deep in time, right? There's almost no continental crust that exists from this time period anymore. So most things are basically like from one place in Australia, or a couple of other places like that, right? So you've got that sort of formation of life in here as well, potentially as early as 4.1 billion years ago, but definitely by 3.7 to 3.5 billion years ago. So primitive microbial life within that time period. As well as entering into the Phanerozoic, which is time period we're currently in now, right? And so this is 540 million years ago to present day. That's when you start to see these major mass extinctions or records of it within the rock. The Cambrian explosion, where life diversified a bunch or seemed to, right? Or at least fossilized better. And then all the way on to climate today, and who knows what we will be doing in the future. Well, I can probably tell you some things about that, and they're not good unless you actually do something about it. So, nevertheless, life on our planet probably formed in the water, right? Water is really important thinking about life. Potentially the ocean, maybe in the deep ocean around things like the hydrothermal vents, right? So this is kind of a possible place where life formed, maybe through chemosynthesis, something like that. As well as potentially also in maybe shallow pools, tidal regions, places where you get wetting and drying cycles. It's not necessarily definitively that it came in the ocean. We know we probably needed water for that, right? But what's really cool about the ocean is several of life's major milestones are associated with it, right? And so it's been this sort of backdrop to all of these changes this planet has seen. And I don't think that's by coincidence, personally, even though I've not done this for very long, so maybe don't take my word for it, right? So we have potentially the origin of unicellular life, right? The origin of life, I'm gonna put this down because we're gonna start crackling. Origin of oxygen and photosynthesis, most likely there's something cyanobacteria-like in the ocean itself, right? Eukaryotes, right? So you have cell nucleus as well as potentially up to multicellular life first before I ever decided to get on land, right? So some of these big things that like lead to us today happen most likely in the ocean first. Sorry, crackle. Okay, calm yourself. No? Yes? No? Ah, okay. All right. So I care a lot about the ocean because of that. So I like to think about it as this incredible thing that's been here for a really long period of time. But largely how I think about it, though, at least in the context of most of the research I do, is as a climate mediator, right? So the ocean is really an excellent storer of heat and a really excellent buffer. So thank you, water, all right? Water is really cool and it's really special, all right? So our oceans are about 70% of the Earth's surface. They support enormous ecological diversity, right? A lot of it we have yet to discover. We can just make some estimates on that. The physical variations in the ocean span a really vast range of temporal and spatial scales, all the way down to things like, microscales, microseconds, that things like thousands and thousands of years, right? And so the heat capacity of water is actually much greater than the heat capacity of air. And then the other important thing is that the density of water is actually much greater than the density of air. And because of those two things, then the ocean can actually store a whole buttload more heat than the atmosphere ever could, all right? And so this picture here is actually, I should put this down, is the energy change in zetajoules since about 1970, right? Of all of the different components of the ocean and Earth system, right? So the Earth system itself. So we're talking about the atmosphere in that purple down there, which you can barely see, right? The land in that orange color there. The ice, so think about the cryosphere, we're talking about ice sheets, we're talking about sea ice potentially, mostly glaciers, things like that, are in the gray there. And then we have the ocean, right? So you have the top, or so the bottom, 2 kilometers of the ocean in the darkest blue, 700 meters to 2,000 meters in the middle blue, and then the lightest blue is the top of the ocean, all right? But all of this is the ocean. Everything else is the rest of the planet. So when you think about heat uptake, this is the heat uptake in different components of the climate system relative to 1971. It's the ocean that's been doing most of that work. And it's because of the nature of water itself, right? But the ocean has actually taken up more than 90% of the excess heat and about 30% of the excess carbon dioxide in the climate system due solely to human activity. All right, so you should wake up every day and thank the ocean that you don't live in a fiery hellscape because it is doing a lot of that work. But when you perturb the ocean like this, it is going to change, right? And not always for the better, right? It's not just a box where you can shove your problems and ignore them, okay? But it is really a heavy hitter, all right? And because of this heat capacity, because of this sort of slow circulations that it supports, we're going to talk about all of that. It mediates climate, especially on long time scales, right? So the ocean is a really, really important piece of the climate system. So you think about your weather, you live on land, and then you breathe the atmosphere, but really the ocean is doing a lot of stuff to sort of make things more hospitable in a way, right? And so the ocean transports heat, it transports salt. Yes, there's salt in it, carbon dioxide, oxygen, and a bunch of other nutrients as well through its circulation, as well as a bunch of other things that are happening with it. And we are going to talk about that. So we're talking about nutrients that are kind of relevant for life, things that help support life, so nitrate, phosphate, silicate, all of these kinds of basic things that life, or at least the base of the oceanic food web, like phytoplankton, zooplankton, depend on, and then eventually kind of up and up and up. Right? And so this is just a plot of sea surface temperature. So it's the temperature of the ocean surface. This is actually in degrees C here. And so what you can kind of notice from this picture basically is that you have your warmer temperatures at the equator and then colder temperatures at the pole. Right? And the reason you have that is because the Earth is differentially heated at the equator versus at the poles. Right? So you get more direct incoming solar radiation at the equator than you do at the poles. All right? And so the ocean actually works to try to balance that out, just like the atmosphere does. So you have more heat coming in, you want to move it to the place where there's a deficit. All right? And so this figure on the right is an image of that, basically what that heat transport looks like. So we're saying, hey, where do we do when we move heat around in petawatts, okay? And so the bottom there is versus latitude, so it's just averaged or basically summed over latitude, right? And then you have the heat transport on the y-axis, okay? And so what you see here basically is that by and large, the total is in black, the atmosphere is in that cyan or light green color, and then the ocean itself is in the blue, right? So the vast majority of the meridional heat transport is done by the atmosphere, which isn't really surprising. Even though the ocean has a greater heat capacity, the atmosphere is just faster, and it can sometimes be a little more efficient at that process, right? So this is pretty typical of our Earth system. This is typical for Earth, right? Except, you know, in the only sort of place where the ocean might actually outdo the heat transport is in the tropical regions, so in the deep tropical regions there, right? So basically, you heat your ocean, it's going to move that heat around, right? Your atmosphere wants to move that around, right? The idea that things are in motion is because they just want to even out all of these gradients that we're creating on our planet, right? What's cool, though, is that you can go one step beyond and think about ocean physics. The chemistry, the biology, and the geology are actually all connected, right? And so what this is a figure of is just ocean chlorophyll in April 2024. So those green colors are telling you basically places where there's a lot of productivity. So a lot of phytoplankton, they're eating up the nutrients, they're growing, they're kind of plants, they're the base of the food web in the ocean, right? They're having a blast here, right? Well, when I look at this picture, not only do I see, these areas that are green, I see these blue areas too, right? So that's where there's just not a lot of life, there's not a lot of productivity happening. And the reason for that is because of ocean physics. So I can look at this and say I can see biology, but I can also look at this picture and say I see ocean circulation, right? You may not see it yet, don't worry. Not a test yet. But there's a lot of ocean circulation that's actually going on in this figure that leads to the patterns that you see. For example, there's upwelling along the equator. So that basically means ocean is rising along the equator, right? So water's coming up from the deep part of the ocean there, because you have divergence here from the way the atmospheric winds are blowing, right? And what that does is it brings nutrient-rich water from the deep parts of the ocean to the surface, and phytoplankton are like, heck yeah, I'm gonna eat that up, and I'm gonna grow, and I'm gonna have a good time, right? So that's why you see that band along the equator, right? Some of these other regions are light limited, right? But in here, what you have are your large-scale subtropical gyres, which are regions of large downwelling, right? So they're not nutrient-rich places, and so life is like, I don't like that region as much, right? So the physics, the biology, the geology, the chemistry are kind of all related to each other, right? And this is not just in modern day. It's likely that this has happened, for, probably billions of years, right? So a nice science article in the last few years. This is an article about Southern Ocean upwelling. So the Southern Ocean is just down here in the south, as you might expect. Earth's obliquity, and then this sort of glacial, interglacial atmospheric CO2 change. So the ocean actually can modulate the amount of carbon dioxide in the atmosphere on really long time scales. And maybe part of the reason that we have glaciations, or at least help support those, by taking up carbon dioxide, right? So it can bring that into the ocean, and it can store it for very long periods of time. Eventually it's gonna let it out. So you have to think about that, right? It's not just put it there and forget about it, right? But it's done this, right? So that's why we worry about these things in the future, because we have some understanding of what might have happened in the past, right? So at the same time, you could look at something like surface oxygen. Let me go now, okay? It's something like surface oxygen, and this is a kind of a cool picture, right? So it's basically saying, what does the oxygen look like at the surface of the ocean? So the ocean takes up things like oxygen as well. Oh my goodness, it does not like that one. Correct.
There might be a short in there somewhere.
Yes.
John did put the other mic.
Yeah, we can always switch to the other.
Maybe it's a good idea for me to switch, because I just feel really bad about this. I feel like it's probably just...
It's been a chronic problem for quite a while.
Okay. So it's not just me.
No.
All right. Okay. So in this picture, right, I see a lot of really interesting things happening here. Okay, you might not, but I do. So you have areas of low oxygen, right? Maybe along the equator again in the surface ocean, then areas of really high oxygen, maybe in the polar regions, right? So what you're seeing here is actually the effect of something called, it's just solubility, right? So the ocean can actually absorb, or seawater can actually absorb more oxygen, more gases, basically, when the temperatures are colder, right? So you can think about climate, right? You can take up more oxygen, not just in the polar regions, but if you change sort of the average temperature of the surface ocean over very long periods, it might actually impact how oxygenated your ocean is, right? It's going to impact the carbonation in the ocean as well, which is also going to be related to biology. So there's a big piece about this that I'm ignoring, which is the biological part of it, right? So biology impacts that as well, and then that feeds back on the atmosphere, that feeds back on the ocean, and down and down and down we go. This is the thing about the Earth system you always have to appreciate and think about is that everything is coupled, right? You change one thing, it changes a whole lot of other things as well. Right, so a couple of different ways in which the chemistry piece, right, comes in, the biology comes in, right, and then we're not going to think too hard about the geology because that's very long time scales, right, millions of years, right, thinking about why the ocean is salty at all, for example. So that's where, salt comes from, is literally the weathering of rocks, right, so that is how we think about that, right. It's a mediator climate, right? And then if we go back to thinking about the evolution of life, there's nothing stagnant about the ocean, right? It's not this background, even though I said it's a backdrop over which things have happened, it has been an active player in those changes, right? And so it's not just that you have water and you can think of it as like a bathtub where it just didn't do anything and everything just came along for the ride, right? And now here we are. And so we have to really think about why and how the ocean moves if we want to appreciate that, right? So the large-scale ocean circulation, which is how the ocean moves, really cares about four things. It cares about the wind, right? Okay, atmosphere blows over the ocean, forces motion, right? It cares about buoyancy or density, so changes basically in the lightness, how light or dense the surface waters are can lead to vertical exchange in the ocean, right? Cares about the bathymetry, so basically continental configuration, but also the shape of the seafloor. That can steer currents, they can lead to mixing over very rough topography that actually impacts upwelling, that potentially impacts the exchange of carbon, all of these sorts of things, right? And we have some really complex bathymetry, right? And then it also cares about rotation. Our planet's rotating, right? And when you make a rotating planet, when you deal with the Navier-Stokes equations in the geophysical fluid dynamics framework, you're thinking about them in that rotating bit. And that makes all sorts of cool things happen, like hurricanes, eddies in the ocean, what have you, right, on very different scales, okay? So part of the reason we experience the things we do in the way we do is because the Earth is rotating, right? It also kind of sets the scales of certain atmospheric features, all sorts of stuff like that. I won't go into detail of that because you don't need to know, right? So the large-scale ocean circulation, from my standpoint, really just has two major components. And so the first is the wind-driven circulation, right? So the winds impact the circulation. So this is a nice picture of Florida and the east coast of the United States. What this is actually just a, this is from a simulation, basically. These are just little colored by current speeds. Here are speeds of the current kind of following little tracers within here of the Gulf Stream, which is a major warm current that brings heat from the equator northward along the U.S. East Coast, right? And so we have a wind-driven circulation, which I'll talk about, and then the overturning circulation, which this schematic I will explain in a bit. It's basically just an average view of what the ocean circulation looks like in the vertical. If you kind of just smash it all together and schematize the heck out of it, just say this is what it is. You have sinking in Antarctica and around the Arctic and the North Atlantic. That spreads into the deep and abyssal oceans, and then eventually it kind of comes up to the surface in the Southern Ocean. Lather, rinse, repeat. So this is that kind of global conveyor belt type circulation, if you've ever heard about that piece. It's called the meridional overturning circulation, or the global overturning circulation, either way. So the upper ocean is driven by winds. This is mostly like the top 1 kilometer of the ocean. You have large-scale atmospheric wind belts on this planet, which are those gray arrows, if you can see that in this figure, that sort of drive some of these currents, right? And then within that, though, these lead to areas of convergence and divergence of water, actually, that leads to a whole host of things, and eventually you get gyres, right? So these are just features, big features that sort of circulate around within the ocean itself, right? So they're the major player of the large-scale ocean circulation. You have some really interesting equatorial currents as well. But by and large, you're probably familiar with a system like this, which would be something like the Gulf Stream, right? This is a western boundary current. It brings warm water to the poles. And then you have that sort of southward return flow that's a little broader. It's actually bringing cold water from the north back down. So this is actually why the Atlantic Ocean, if you go to the East Coast, and in the ocean, it's relatively warm. But if you go to the West Coast, California, you're bringing cold water from the poles. It sucks, it's cold. If you've ever been in the Pacific Ocean on this side of it, if you're not far enough south, it's unpleasant. So this is actually just related to the large-scale ocean circulation. And the gyres you may also be familiar with from things like maybe the Great Pacific or Atlantic garbage patches that sit in the middle of them, right? Because they're these kind of big circulatory features, right? Things get trapped inside them. So there's these enormous areas of trash that sit in them now. That's where our plastics and all sorts of things that don't actually degrade over time go. And that's part of the reason why there's just basically microplastics in like everything now. But also it sits there like that, right? So, you know, we make our own imprint on these kinds of features here. Other interesting things are, you know, the Antarctic circumpolar current, which just basically flows constantly around Antarctica. And basically unimpeded. It's a really, really cool current. It's an area of really strong upwelling as well within that. And so that's the wind-driven circulation. And then this is our, oceanographers really love really complicated schematics. This is the global overturning circulation. All you really need to know about this, basically, is that you have this circulation that's driven by differences in density. So what is happening here is you have changes around the Antarctic, right? So along here, and in the North Atlantic that basically lead to water that gets denser. And so all I really mean by this is basically it gets colder and it gets saltier in those regions. You're moving it toward the poles, right? That's where the ice is, right? When you freeze ice, it rejects the salt, so ice likes to freeze fresher than the surrounding water, and so leaves that salt behind. And that actually leads to water, that water is actually denser than its surrounding environment, so it sinks, right? And so then you actually get this sort of large, very long time scale circulation that we call the overturning circulation, right? So it comes from the North Atlantic, and it goes around here, it might spin around the Southern Ocean for a bit, come up, you know, through here, through the Indian Ocean, and eventually into the Pacific, and back, right? But the whole point of this is a very slow time scale circulation. You know, wind-driven circulation are things that vary on the order of things like days, months, years, you know, interannually. And the overturning circulation is something that's more like centennial to millennial timescale. Right? So it takes something like 1,000 years for something to complete the loop, which would be to go through this whole conveyor belt type of thing. That doesn't actually mean that's what happens, so it's not like this is just a current system that's doing this, right? This is just what it looks like on average, and it's an average explanation of how the water moves, right? But it's not the same as like you could go out and you could measure the Gulf Stream as like an actual wind-driven current. Okay? But that's okay. The point is it still has this really strong impact on the ocean, and it's really, really important for connecting the surface ocean and changes that happen in the atmosphere to the deep ocean, right? And so how that is communicated is largely, so how do things that's communicated to the deep ocean is through these changes at the poles, right? And they're communicated directly through the deep and abyssal ocean by forming that dense water, okay? And so when you form dense water, it basically takes the imprint of whatever the heck is happening in the atmosphere with it, takes it and brings it down into the deep parts of the ocean, right? So this is actually how you do that uptake. You have air-sea gas exchange, right? Something like carbon dioxide or oxygen. And then eventually that water sinks and is no longer in contact with the atmosphere. So it kind of has an imprint of what things were when it was last at the surface, right? And then it goes through a bunch of changes, biology, and all the other sorts of things, right? But what this is basically is we have these two things we have these things called water masses in oceanography. And in the North Atlantic, we have something called North Atlantic deep water. That's that dense water that's formed in the North Atlantic, right? And that forms that limb of the overturning circulation, right? And so what this is just showing you in the very deep parts of the global ocean what the fraction of North Atlantic deep water is. And so this is, blue colors mean almost all of that water in the ocean just came from the North Atlantic, right? And then the yellower you get, mean less and less of it is, right? So in the North Atlantic, unsurprisingly, North Atlantic deep water has this very strong component in the North Atlantic, right? And it's a major component of that. This is what Antarctic bottom water looks like. So this is the water that's formed in specific places around Antarctica, right? So we've got a really high component of Antarctic bottom water in the deep ocean, especially around Antarctica, but almost above about 50% of it across the entire Pacific Ocean, across the entire Indian Ocean, into a good chunk of the Atlantic, right? So you can imagine, if you make changes around Antarctica, you actually make global change happen in the deep ocean, right? That's really important, right? So that's how you bring those features into the deep ocean, or through these very specific pathways, right? So really cool thing to think about. Those are kind of the major pieces of the circulation that we have within the ocean. It's a lot going on, and so I don't expect you to kind of pick up on all of this all through this whole thing, right? But I'm going to change gears here. Like I said, Earth is a coupled system, so the ocean never really does anything in isolation. The ocean, the atmosphere, the ice, the land, the chemistry, the biology, and the geology, all of these things are always interacting and feeding back on each other on timescales of things, like I said, milliseconds, microseconds, to millions and millions and millions of years, right? So anytime you try to study a process, you really have to know a lot about what you're thinking about to make sure you really understand all of the ways in which it can be impacted, right? So you study the ocean, right? You know, a lot of my job is just studying one specific part of the ocean, because I can spend a whole career just doing that and I still wouldn't know everything about it, right? So not even the whole ocean, right? Which I always think is really, really cool to think about, right? And so when we think about coupled systems, though, and this is where we're going to start thinking about exoplanets then, is if you think about an exoplanet that has an ocean, right, potentially, right, or has an atmosphere, right? If we really want to understand the life potentially on that exoplanet, or just understand how that exoplanet works, we need to take this Earth system way of thinking and apply it in that new context, right? So this is really, really important. Earth scientists are the OG planetary scientists. I don't want to be a jerk, but like, we studied the Earth first. And we know a lot about it. Yeah, there's tons and tons of mysteries, tons of things we don't know, but there's stuff that we've learned and knowledge that we've built up over time that we can use and apply to exoplanets without having to reinvent the wheel, without somebody having to rediscover seasonality on a planet because the planet's tilted on its axis, right? Like, there are things that we can take in the lessons we've learned from Earth and then think about those in a broader context. And that's kind of what I want to do when I think about exoplanet oceans. It's like, what do I know about Earth's ocean? What are the assumptions I've baked into thinking about Earth's ocean in particular? And then how do I go a step back and think, all right, what do we do when we start back from square one? When you're like, okay, I have an ocean. Some kind of ocean that's not necessarily the same continental patterns, or not necessarily forced by the same mechanism. How do we go back and think about that? All right? This is hard. So at the end of the day, the nice thing is that as far back as you really maybe need to go is thinking about the fundamental physics, right? So the physics that describe fluid motion on any planet are largely the same, right? Think about Earth, think about Jupiter. Even though like the constraints are different, right? You're still doing Navier-Stokes, you're still doing your GFD, right? But of course the devil is definitely in the details, right? That's where, you know, certain Earth-based assumptions might not be appropriate. But of course we make them because we're on Earth, right? And we're studying Earth, so, you know, it's not a problem, right? Like Navier-Stokes still applies to Jupiter, just rotating a lot faster, and it's got some heating from below and some other things that are, you know, what, it's bigger, right? And it's made up of different things. And so when you start to think about how these things move, it's still, okay, the physics is still there, but you have to go back and be like, what are my assumptions, right? What are the assumptions that are not appropriate on this planet that would be appropriate on this planet, right? So think about Venus, right? And its atmosphere and the fact that it's slowly rotating and all these sorts of things. How does that actually impact then what that circulation looks like? So super cool to kind of think about. And so people do think about this. I am definitely, by and large, not the only person who thinks about exoplanet oceans. I've thought about it for some time. There's this really nice paper in 2019 by Yang et al. And colleagues, where they were thinking about ocean dynamics, specifically ocean circulation, and the inner edge of the habitable zone, right? So thinking about the habitable zone around the host star is basically where your exoplanet can have liquid water on its surface, right? So it's a range of distances where you can potentially support liquid water on a surface of a planet, right? So they're thinking about this in that inner edge, so the part that would be the closest part to the star where you could still have liquid water on the surface of an exoplanet for something that's tidally locked. And terrestrial, right? So terrestrial meaning Earth-like, basically, or Earth enough, there's land, there's an ocean, whatever, right? Tidally locked, I think most of you would probably know that, right? It's like the moon, where one face is always facing the host star in this case, rather than Earth. And so what that means is you only have you have a day side, and you have a permanent day side and a permanent night side to your planet. All right? And the only reason I'm really bringing this up is because what they did was a bunch of simulations here across all of these things. And they have like And that top figure is day to night oceanic heat transport in the top and the bottom. Global mean surface temperature, so the average temperature of the planet. So you're thinking about climate in that way, just like we think about global mean temperature on our planet and how it's changing, right? And then also the surface temperature gradient, which you don't need to worry about. So those top two there, the red line is basically a fully coupled climate model that has a dynamic ocean. So they basically took a model of the Earth, they took an Earth system model and just adapted it for this exoplanet, right? So we have big hunkin' climate models that we use to ask questions about how the Earth might change in the future. That's what we do. But people are like, heck yeah, let's just try to like rip out some of these baked-in assumptions from these models and apply them in this different context, right? So they took this pretty well-known model here, and then the blue line is just when you have the atmosphere and not a dynamic ocean. So basically, you treat the ocean as a slab or a bathtub where it can just exchange heat, but it's not moving. It doesn't really. It's just a boundary condition, right? So not like the real world, right? And what they found basically is that you get this huge difference between those red and those blue lines when you have a dynamic ocean, right? So the ocean as a mediator for climate, even on in this particular case of this habitable zone of these tidally locked terrestrial planets around these particular stars, right? You get really big changes in actual global mean surface temperature. So you're actually warmer, for example, when you have a dynamic ocean, right? Quite a bit warmer. Right? So this is something like going from, and these are as a function, sorry, I should have told you this, as a function of different installations, so different radiation that the planet receives at its surface. So something like 1400, this is Earth that we receive is about 1367 watts per meter squared, so they're the very low end of this. So these are pretty high, highly irradiated planets, right? So this is in watts per meter squared here. So what we receive would be on the very far end of this. And what they're getting is a global mean surface temperature in the atmospheric case of something that's like basically below freezing, so this is in Kelvin, right? And then something that is significantly warmer than that by 20, 30 degrees, right? So you can just warm up your planet by actually including ocean dynamics in it, which is pretty nifty when you think about it, okay? So people are really trying to think about this, but it's hard because these problems are so unconstrained, right? When you think about exoplanets, again, nobody can prove that they actually have oceans. Right? Like I said earlier in this talk, you can't direct image an ocean, you can't kind of go through that, at least not yet, have worlds one day, come on, please tell me. You can't do that yet, right? But you can use internal structure modeling based on mass radius relationships, things like that with these planets to figure out whether they might be able to host oceans on their surfaces. And when they're in the habitable zone, right, then they probably can have liquid water, which is really cool to think about. And those are often the targets that people want to use for follow-up surveys with like JWST or things like that to kind of potentially look at these planets' atmospheres for biosignatures, okay? So oxygen being a big one, but oxygen comes without it. Most of the biosignatures that we have are things that could also potentially be created from non-living things. That's where the chemistry gets really interesting. But if having high levels of oxygen may be an indication, for example, that a planet actually has life on it, right? At the level of oxygen like we have today, which is about 21% of our atmosphere versus 0 like it used to have, right? And it's that way because life. Right? Because of oxygenic photosynthesis, right? So life fundamentally changed how our planet is, which I think is also really cool. Earth is a living planet in that sense, and it almost always has been. Okay? So the next thing I think about is what might be different about oceans on other worlds. Well, everything. I mean, like I said, these problems are really cool to think about, and they're really fun, but they're super unconstrained, right? You've got one data point or like 2 data points, or basically what you have is you're like, I think there's an exoplanet orbiting this star that could have an ocean. And I know probably what the stellar flux reaching that exoplanet's surface is, and I know maybe its rotation rate and how far it is away from its host star. The rest of it, with Webb, you can at least figure out what's potentially in these things' atmospheres, right? And so that's where like Earth atmospheric scientists and oceanographers and folks like us come in, because we can tell you how it moves. We can tell you the radiative properties of that. We can tell you, how feasible it is to have something like that, right? Because we think about this all the time, which I think is really cool. But, if you're going to start thinking about an exoplanet with an ocean, you're like, how would I model this? Some good things to start from would be the equation of state, right? So the equation of state literally is just describing the density of seawater. So equation of state for, you think about the ideal gas law maybe you're familiar with for the atmosphere, or most things, if you've done any kind of physics. If you haven't, don't worry about it, right? The equation of state for the ocean is a highly nonlinear empirical mess. The only way we know about it is because we've gone out and taken measurements of the ocean, right? And it's that way because seawater, the density of seawater doesn't just depend on temperature, it depends on salinity, right? So salt makes the ocean behave in some really, really interesting ways, right? So does your ocean, what is your ocean made of is probably the first question you might want to ask, okay? So you're like, maybe it's got liquid water. Could it have salt? I have no idea. So you have to think about where this planet may be formed in its particular place in the galaxy, right? Where did that star form? What things could have been delivered to it. And I'm actually on a research forward project that's thinking about these Hadean planets, which are these potentially big ocean-covered worlds, like fully ocean-covered worlds with very hundreds of kilometers deep oceans and hydrogen helium atmospheres. So that's a thing that we're working on with Y-Core right now. So if there's water, is there salt? Or is there something else within that water that might actually fundamentally change its density structure? Because if you change the density structure, you change how the ocean moves. So again, this is why this is hard. You need to think about surface forcing, right? And also deep ocean forcing. So geothermal heat flux, right? So you actually have a very, very minor amount of heat flux that comes from the bottom of the seafloor that tries heat to the ocean. We largely neglect that in climate modeling just because the incoming solar radiation is the bigger piece of that, right? But that may not be the case on other planets, right? Maybe your planet has just cooled off and formed its ocean, like on the early Earth, right? And it still needs to get rid of a whole buttload of heat somehow, right? So you have to think how much heat, how much fresh water, right, reaches the surface, and what's the horizontal distribution of those properties, right? So if you have a tidally locked planet, right, it's getting a whole bunch of sun on one side of the planet, not sun, star, sorry. But if you rotate it like Earth or anything else, right, it's going to be sort of more uniformly distributed, and that's going to change basically how the atmosphere and the ocean behave, okay? And then we can think about the large-scale ocean circulation. And so we'd have to ask, is there land? So land boundaries are something that sort of helps support certain types of circulation. They're an important part of actually what helps us support those large-scale gyres that we have. Maybe there isn't land. So maybe you're going to actually have an ocean circulation that looks kind of like how Jupiter's atmosphere looks, right, with the belts. What's the bathymetry? You have no idea. You don't know, right? But bathymetry really, really matters for our circulation, right? And it matters then for the uptake of these nutrients. It matters for life. Do you have really strong tides, right? So tidal forcing, right? So think about the moons around Jupiter or Saturn, right? So Enceladus or Europa. They might have liquid oceans because of that tidal flexure, right? We're not just thinking about that. When Earth first formed, and this is something that I'm really interested in, is the moon was a lot closer, which means the tidal forcing on our planet was a lot different back then for our ocean than it is for today's ocean. Tidal diffusivity changes the shape of the overturning circulation. It changes the nature of it. It warms the abyssal ocean, right? So those are all things that could be really different. Is there significant ice cover, right, to reflect a bit of that incoming solar radiation, right? Think about Enceladus, Europa, fully ice-covered moons, not really much of an atmosphere, right? So they're not going to have wind driving their circulation. But maybe you do have an exoplanet with an atmosphere, and it's not that ice-covered, or it's only a little ice-covered, or whatever, right? That's going to impact a lot of different things about the planet. And then you want to think about things like rotation rate, right? So there's these sort of external parameters, like the size of the planet, its gravitation, all of that, right? All the way out to how thick is the atmosphere? So what is the atmospheric pressure at the ocean's surface? Because that's going to impact how much momentum is fluxed into the ocean and how it moves, right? So this is endless stuff that you can go through. So when you're thinking about modeling these kinds of exoplanets, you have to really be thoughtful about how you're constraining the problem, right? So like I said, we use Earth system models. A lot of what people have done is just taken Earth system models and hacked them up and built something out of them that can be adapted in a lot of different cases for exoplanets. So something like the exoplanet community atmosphere model, which is an actual atmosphere model that was built for an Earth system model that they took and adapted for different radiation schemes for the incoming. Instead of just the sun heating a planet, right? You could have something like Proxima Centauri or any other pick your star, right? And then you could maybe have different constituents in the atmosphere, which is going to affect the radiative properties of the atmosphere, how much heat reaches the surface of the ocean, and endless. So usually when you take climate models, you're really only going to deal with like an atmosphere and an ocean and maybe some sea ice, because, getting into details of like land biogeochemistry, it's not helpful. Right? We're not at a level where we can ask those kinds of questions yet of exoplanets. But you can take some of these basic things that we have and use them in a different context if you're thoughtful about it. So that's actually what I started to do with some of my undergrads. So this is work that's from Ivana Chevalier, who's one of the undergrads in my research group. She's leaving me soon. She's going off to graduate school, though. Very good. And so she'll be starting at NC State in the fall, although she will be in earth science, oceanography realm. So this project, what we've been doing is we used a couple of climate models to sort of simulate the climate on a Proxima Centauri B-like exoplanet, right? And so this is a planet that's tidally locked. It has an 11 Earth day year and an 11 Earth day day, right? So it's slowly rotating, right? But it's very close into its planet. Proxima Centauri itself is a cooler red dwarf type star. So that round of installation that planet receives is actually less than what Earth receives, even though it's much closer, farther from the sun, right? So there's only an ocean and atmosphere in here. There's no land. We have this much less than on modern Earth. And then what we're doing here is all we're going to do is we change some different parameters and say, okay, what happens to the ocean circulation or sort of the heat transport, that meridional heat transport on this planet if we change the ocean depth? So we have a really shallow ocean first, and then we have a deeper ocean. Modern Earth ocean is on average about 3,800 meters, so a lot deeper than what we're showing here. And there's some really, really deep parts of the Earth's ocean, but irrelevant for this, right? And then what happens, like I said, if you change the installation? So you go from having Proxima Centauri B, Proxima Centauri is your star, to having the sun there instead, right? So versus 1360. Right? And so as a friendly reminder, this is the figure of modern Earth, what the atmospheric and oceanic meridional heat transport looks like. And so typically what you see is, like I said, you have this strong meridional atmospheric heat transport that dominates the total heat transport. But when you do that in this particular simulation, so what we've done is on the top there is that same meridional heat transport. And this is in this Proxima Centauri B-like planet, right? And so you have a shallow Earth-like planet, so it's got the Earth-like installation, right? So it's got the sun and a shallow ocean. And then we have the same thing, but with a deep ocean, and then the other one is Proxima Centauri, right? So the 840 watts per meter squared, so less insulation. And in all of these cases, the red line is the meridional atmospheric heat transport, and then you have the oceanic heat transport. And by and large, what you actually see in this particular case is that when you change the depth of the ocean, you change, in some sense, the meridional heat transport, right? And so it's actually partitioned very, very differently from what it is on regular Earth, right? So suddenly you actually have the ocean doing a lot more of the work in this meridional direction. Now, on a tidally locked planet, that longitudinal, so day to night side transport in that direction is also going to be really important. It's just that this is something for me that I think is really interesting because by and large you just don't see, at least from my perspective of studying Earth for such a long time, something like this where the ocean is doing more of the work than the atmosphere. And I'm not going to dig into the details of why that is, but it is actually largely related to sea ice cover. And so what you get here is, this is ice cover, so sea ice in these different simulations. So when you have a shallow ocean, you actually get sea ice formation, so this is longitude versus latitude now. This is the night side of the planet. So you get a very specific pattern of sea ice forming. And what's really cool about this is your ice is not forming in your poles, right, like it does on Earth. The coldest part of your planet is on the night side, right, opposite from your substellar point, on the equator, right? We do not have ice at the equator on Earth, right? But you do on this, right, because of the nature of that tidal locking, okay? And it's this ice that actually kind of leads to this compensating pattern where the atmosphere ends up doing less of the heat transport than the ocean does. But again, I won't get into the details of that. It's actually kind of complicated to explain. But
these are just some of the things you can ask. Like I said, these are a bit esoteric questions and things I'm just interested in as an oceanographer, but you can ask, more detailed questions about ocean circulation and its connection potentially to biosignatures and life as well. I know somebody who's doing some really cool work about changing planetary rotation rate and how that impacts how oxygenated the deep ocean is and how that might be important for planets that might have complex multicellular life that depends on that, right? So really cool research that's going on throughout. It's been really exciting, I think, to see over time this stuff grow into really, people really trying to do this. Like I've been thinking about wanting to do something like this since I was a graduate student, which is 10 years ago now, long time ago now, and just never really having the courage to take that step. And so I am finally doing that, and I'm really glad that I can. So I'm going to leave it there because I think I've really definitely talked your ears off. Oh my gosh, it's 8:30 almost. Sorry about that. I can go forever, but thank you very much. And if you have questions, I'm happy to answer them. And you can ask me basically anything. It could be about this, it could be about my life, it could be about other stuff you're interested in. If you want to know about atmospheres, I did bring my partner, who is an atmospheric scientist and a professor also in my department, because I've been slowly roping him into thinking about other atmospheres as well. So all of our knowledge is relevant. It's pretty cool. So thank you very much.
Yeah, first of all, thank you. That was an excellent
Thank you.
presentation. So the question I had was, so there seems to be a substantial amount of heat transfer sort of from the atmosphere into the ocean surface.
Yeah.
I guess what I was wondering, is there a substantial amount of heat transfer from the Earth through the bottom of the ocean, like from the, from the mantle through the crust?
So there isn't any more. But there is some, right? So I don't have a good picture of the symmetry truly. Let me find that one awful one that I have. Let's see if I can find it in here. All right, so you're probably not going to see this, but these, I don't know if you can see this light color kind of line through here. So this is the mid-ocean ridge. This is basically a chain of mountains that sit along the Atlantic seafloor. And it's actually a place where the continental plates are spreading apart. Right? And so you actually would get, you also have this, like the East Pacific Rise, any of these kind of major bathymetric features, bathymetric features are going to have that, right? And so there are actually areas where you are getting sort of additional heat flux from the, my goodness, the core that basically below the crust of the planet, right, into the ocean. Again, it's relatively negligible today compared to the amount of incoming radiation that the ocean receives from the surface. I don't know the numbers off the top of my head, but like the incoming shortwave radiation that reaches the ocean surface is something like 200 watts per meter squared on average. And so the big things, the ocean's really largely heated from above in this context. But again, there's, like I said, maybe in our steep past when the planet is still cooling significantly, that will matter. And it would definitely matter on other exoplanets where, again, you have some other kind of activity. There can be radiogenic stuff. There can be all sorts of stuff you could think about. But on Earth today, not so much.
Anybody else?
Just want to make the observation. I took a little physical and chemical oceanography when I was in graduate school about 20 years ago. And I think back to those classes and I watched this presentation about how you can apply these models to exoplanets. And I think just the idea then would have been shocking.
Yeah. Yeah. I think even back then when I kind of thought about doing these things, it seemed, and this was like, so I was in graduate school, 2011 to 2016, it seemed like maybe a little out of reach. Even though at that time, Kepler and things like we were doing exoplanets a lot. You'd been doing that for like 15 years. So definitely, I think part of it too is that Earth scientists are very much focused on understanding Earth, and it's hard to sometimes get them to look outside of that and think that these things are applicable elsewhere. But
it's cool that it's changed though. Like suddenly it's kind of exploded, and I especially in the past like 5, maybe 10 years, I think since I graduated. But I wasn't really steeped in that at the time. But definitely in the last 5 years, people are like, holy cow, we can use we just do climate models and go for it. And I think that's like, I think once people have torn the lid off it now, and now I think it's going to go crazy now. Like it's going to get real wild. Things got real wild with exoplanets, right? And that's not the only part of astronomy that matters by any means. But it's such a cool thing to use. I think what's hard about it from a science perspective is, like I said, it's so unconstrained. It's also so hard to be like, well, how realistic is this? Am I kind of just making shit up? Like it feels a little bit like
it's
that
so poorly
sometimes.
constrained.
Yeah. And so it's cool from like a sandbox perspective. It's like, okay, what can I learn? And so you have to be very thoughtful and very methodical about how you approach the problem. So often people will do like a really coarse resolution model that you can run really fast on like a laptop or very few computing resources, and do a big parameter space exploration where they're like, okay, what if I do a bunch of different rotation rates, a bunch of different things, and then see the patterns from that to maybe say something about what kinds of exoplanets we might want to look at versus not,
What would be really exciting is if predictions come out of those models that we can observe.
I know. Like people like to can potentially use Earth system models as a way to be like, okay, if we had an Earth system model in this kind of state, could we actually tell if we looked at Earth like it was an exoplanet? So basically take, the output from a model, turn that into like an actual atmospheric spectra that like JWST would see.
Yeah.
Can we actually detect the things we think we can detect in the atmosphere, and could we tell that things were living on it? It's hard. No. I mean, you can detect the things in the atmosphere, but like the life piece of it is hard because the chemistry part. And anytime anyone brings up something that's like, this could be this could be a biosignature, it's like, well, it might also have this other pathway. So I wonder, what I'm worried about is that I think with exoplanets especially, I think there's going to be stuff that's like, this planet probably has life, but unless you can like direct image it, I don't know that like from an exoplanet perspective, if people are really going to like truly accept it, because like scientists, we love to be skeptical. That's our jam. And so I think if we do find it, it's gonna kind of need to be in our backyard. I mean, even with like the phosphine on Venus stuff, like Sarah Steger, we talked to her about this when she visited YCOR last year, got dragged for that by the community, like dragged, And so, when we think about like Enceladus or Europa, it's like, how are we gonna figure this out? Are we gonna actually find microbial life in the plumes that are blowing stuff out into space? Or like, are you going to do, I know Europa Clipper's going, and I'm so excited.
So that was my question, is Europa Clipper, it's going, it's on the way. But that model is going to be very different than what an Earth-like model might look like. How would we think of an ocean that would be more like that than an Earth-like model, and how would that data from Clipper apply to other exoplanet research in the future?
So, in that case, like I said, the biggest thing is that you have, instead of an atmosphere an ocean that's forced by, wind, or even, there's maybe some buoyancy driving depending on that ice, right? But there's like a really thick ice, it's an ice sheet, it's not just a shell. We call it a shell because it's going to be thin compared to the ocean, but like from Earth perspective, it's like many kilometers thick. Like ice sheets on Earth are like, like it can be like 5 kilometers thick, like it's a lot. But it's not as much as probably what's on these planets, right? Or, icy moons. In that case, what you're really focusing on for the circulation, and some people have actually done this work out of Caltech a little bit, at least for Enceladus, is like, what kind of circulations could you support? Could you support an overturning circulation? And I think what they do is they kind of invoke like maybe some dense water formation through brine rejection from that ice formation still in the icy shell, tidal flexure largely from Saturn or Jupiter, right? That's going to warm your ocean. And then I can't remember if they have a subsurface, like a geothermal type heat flux. They might invoke that. They probably assumed it didn't have bathymetry, but whatever, that's okay, right? And try to think about it like that. So there are like very simple models for it. that would say like, okay, and then they make an assumption too about what salts might be in the ocean. And they're pretty sure that Europa, at least for Europa, has salt in its ocean. It might just be magnesium sulfide instead of like, our table salt way of living. Magnesium, I'm really not a chemist. But it might have a slightly different type of salt. But I think they figured that out, right, because they did measurements of the magnetic field and the perturbations of the magnetic field. They were like, oh, holy crap, there's probably a salt ocean because salt is conductive, right? So we measure salinity in the ocean through conductivity, by and large. Or we literally just evaporate the seawater and be like, this is how much salt is in it. But both of those are options, right? So they figured that out, and then they went and they basically took our basic GFD principles and then tried to kind of build some like really not super complex Earth system model, but like a model in that way to think about that. And so the lessons we maybe would learn from these for exoplanets is like, especially if you have ice-covered exoplanets, like how do those behave? How does that, ice-covered worlds versus non-ice-covered things, and this is something you can see on Earth as we change the Arctic Ocean to an ice-covered versus ice-free world in time, is that the ocean behaves very differently, right? There's suddenly more exchange between the atmosphere and the ocean. There is less albedo, right? So less reflectivity at the surface as the ocean warms. You're not going to make the ice go away probably on an exoplanet that's fully covered in ice like that, right? But these are things that you would try to think about, basically, is how do you force the surface, right? If you're through, maybe you do have an atmosphere, but if you have a really thick layer of the ice, the ocean and the atmosphere are effectively decoupled, right? So they're not necessarily going to talk to each other unless they can talk through the ice and through its time scales of change and motion. Ice sheets are in motion, they're just really freaking slow. They're non-Newtonian, slowly moving, care about tensors and strain and stress, right? Because they move as a thing, but they are moving. And so you have to, that's when you really bring in like your ice sheet people. So we have folks in geosciences and geology and stuff who are kind of interested in that piece from the icy world's perspective. So sorry, that was a really long-winded response. Okay.
I wanted to go to the point you just made, and interdisciplinary approaches to this. How much interdisciplinary stuff is going on? You've mentioned Y-Core a couple of times. Are there chemists? Are there physicists? Are there atmospheric and oceanic scientists with astronomy people who are really doing a lot more collaboration now than maybe even when you were in graduate school?
Yes, definitely. So Y-Core literally is that. And so it's been really cool to be a part of that. So the reason I'm involved in Y-Core at all was when I arrived, they were doing this Origins of Life cluster hire on campus, and they put me on the hiring committee. And so, has Thomas Beatty given a talk here? And like, I think somebody mentioned, and I think his wife is giving that talk about black holes and quasars, but coming up. But and him and Juliet Becker and a couple of other people they hired for this to kind of try to think about these problems. And so like I ended up on this committee with like some people they had hired previously, like Susanna Whitakus-Weaver, who's an astrochemist, and then Betul Kachar, she's in bacteriology, but she actually thinks about like origin of life on our planet from that sort of more biological and biochemical perspective. And so when Susanna came here, she was like, we got to do Y-Core. This is what I really want to do. I want to bring all of these disparate pieces from like people who think at the largest scales of the universe and the people who think about the smallest scales of life on a particular planet, right? And so I got to do that because I did the cluster hire and I made friends with them, and then I just kept showing up to their events. After the fact, they were like, we're doing this astronomy thing. And I was like, I'm gonna go, I don't care, I'm gonna crash this party until they accept me. Because I realized like, if I didn't do this now, I was never gonna do it. And so a part of it too is I started to realize that like, astronomers and all these other folk, you need this Earth system perspective. You need that physical perspective about how things work, right? Every single one of us, whether you're a biologist, a chemist, an astronomer, an earth scientist, and even in the different areas of earth science, like geology versus, ice sheet dynamics versus ocean like I do, we only have one piece of the puzzle. And so we cannot answer this question without each other.
you know? And oftentimes we learn how stupid we are in regard to somebody else's field, right? Like I said, I've seen people rediscover seasonality on exoplanets, and if you just talk to somebody on Earth, you wouldn't need to. I've seen us as atmospheric and oceanic scientists rediscover freaking calculus sometimes, or some random statistical technique that mathematicians have known since like the dawn of time, but you just forget, right? And so Y-Core is about actually bringing us together to talk about those things, and we are doing the best we can. I mean, it's pretty early on in its infancy, but I think we're going to grow some really cool stuff out of that. And I am a big proponent of making sure, like I said, AOS is a part of that, because I think traditionally it hasn't been. It's come, mostly astrobiology has come from the biology side, or thinking big astronomy scale, like, okay, there's an exoplanet, there's got some stuff in it, maybe this could happen, and we're like, actually, that doesn't make any physical sense from an atmospheric perspective, right, or from an ocean perspective, right? So we're here to help constrain each other. Just like I might say some stuff about biology that's probably totally untrue, I don't know, you know? So it's hilarious when you put us all in a room together, like, I'm like, yeah, and then we're going to do this chemistry, and Suzanne's like, that's not chemistry, you know? And I'm like, okay. And so like, what we think the other people do, like we're still learning how to talk to each other and translate. And when I say model, I mean a completely different thing than when an astronomer says model. Yeah. Like, so the words you use do not signify the same stuff.
Right.
And so you have to really get good at just laying it on the table, be like, I have no idea what I'm talking about, but we're going to learn this together. And I think it's just been really validating for me to do that and to have a group of people where I feel like I can learn with them, and that together we can build something that's so much greater than any one of our individual parts. So, yeah, Y-Core. And yeah, I never thought I'd be doing it, so here we go. Just have the courage to show up and keep showing up. That's my lesson. And also thank the ocean every day that you don't live in a fiery hellscape. Yeah. Yes, exactly. Mm-hmm. Thank you.
Well, Hannah, this has been a very fun and thought-provoking presentation, and I think the next time we hear some big news about exoplanet research, or see the next program on NOVA about exoplanet research, we're going to be a lot better prepared to kind of ask some critical questions about, you know, what
I really want to be on NOVA. That would be, you know, you grow up watching that, and I hope it'll still stick around. But you grow up watching it, and it's, you know, it really changed my life. Like watching NOVA in nature since I was a kid, like, and I saw the that's why part of the reason why I do astronomy is I saw like the astronomers, and they were so engaging, excited about what they did. Some of them, and I was like, I'm gonna be one of them people. I'm one of them crazies out there telling people, and now I just do it with the ocean. So.
But you're one of those crazies
who's bringing it.
Because what I wanted to say was, where were professors like you when I was an undergrad? In all sincerity.
Thank you very much. I'm not gonna lie. I am a pretty good professor. You can tell. Thank you.
And on behalf of Madison Astronomical Society, I would like to present you with this very nice Madison Astronomical Society branded coffee mug that does not necessarily have to hold coffee.
But that's fair, you know?
Hannah, it's been a pleasure, and thank you very much for being here tonight.
Thank you very much. I really appreciate it. Thank you all for listening. I really need to keep you so late. I appreciate it. I hope you learned something. If you have questions, you're always welcome to email me or reach out to me via this. I really do mean it. Maybe one day I'll actually show up and crash your party more often. Watch out.
Yeah, we have our meetings here on the second Friday of every month, and the next one's coming up on August 8th, so we hope to see you then. Yes, Rick?
You heard about the star parties, right?
I did. Yeah. We're gone on October 3rd, and I'm really sad.
Well, but every month.
Okay, because I would actually really like to do that.
Yeah, the monthly ones are for Madison Astronomical Society.
And their guests.
And their guests.
Yes, I'm going to be your guest.
If you brought your checkbook, Jurgen's here.
So, that concludes this month's meeting of the Astronomical Society, and we'll see you back here again on August 8th. Good night, everyone.
Get home safely. Don't let the weather bite you in the butt.
I think you have